Hey everybody! Day 19 of the advent of cyber. Today we're going to look at hardware hacking, the widgets that go brrr. Let's jump into it. Let's get over onto our box. Alright, today we are going to do a lot of reading when we go through this because there's a lot to understand, and it's mainly conceptual and then understanding what it is that we're doing. So, scroll on up, and we're looking at day 19 hardware hacking, Wiggles Go Brrr, spying on Santa. Elf McSkidy was doing a regular sweep of Santa's workshop when he discovered a hardware implant. The implant has a web camera attached to a microprocessor and another chip. It seems like someone was planning something malicious. We must try to understand what this implant was trying to do. We will deal with the microprocessor and the web camera in the future tasks. But for now, let's try and uncover what the other chip is being used for. Alright, the VM, or the virtual machine that is used in this task, takes approximately 8 minutes to start up. Holy smokes. We suggest that you start the machine now to have it ready when the time comes. So let's go ahead and click on that start machine. Let's let that thing fire up and let's continue on reading through. Okay, the learning objectives for today are how data is sent via electrical wires in low-level hardware. We also look at hardware communication protocols, how to analyze hardware communication protocols, and reading USART data from a logical capture. Welcome to the Matrix. Hardware hacking is often shrouded in mystery and seen as a super complex topic. Sure sounds like a super complex topic. While there are a lot of in-depth complex hardware hacking components, getting our feet wet is actually pretty simple. Computers today are incredibly powerful. This allows them to build additional features and safety measures into their communication protocols to ensure that messages are transmitted reliably. Think about the Transmission Control Protocol, or TCP, which has multiple redundancies in place. It even sends 3 full packets just to start its communication. In the world of microchips, we often don't have this luxury. To make sure our communication protocols are efficient as possible, we need to keep them as simple as possible. So to do that, we need to enter the world of zeros and ones. This begs the question, how does hardware take electricity and generate it into a signal? In this task, we will be focused on digital communication. For hardware communication, we use a device called a logic analyzer to analyze these signals. The device can be connected to the actual electrical wires that are used for communication between 2 devices that will capture and interpret the signals being sent. In this task, we will use a logical analyzer to determine the communication between 2 devices in the rogue implant. All right. What is an electrical heartbeat? Back to our question. If we have electricity, how can we generate a digital signal? The approach most hardware components take is to simply turn the power on or off. If the power is on, we are transmitting a digital 1. If the power is off, then we're transmitting a digital 0. That's simple enough. We call these ones and zeros bits. To perform communication, we simply turn the power on or off in a specific sequence and transmit a bunch of ones and zeros or zeros and ones. If we send 8 bits, we are sending a single byte. Voila! We have just performed digital hardware communication. These are the wonderful squiggly lines you would see on the logical analyzer. So this looks like what we're going to work with. That's a logic analyzer. Let's go ahead and scroll down. We can transmit text data by using the ASCII table sending the binary representation of each character, we can transmit data. However, it isn't actually just that simple. Well, why would it be? If we wanted zero effort in our communication, we would need an electrical wire for each 0 or 1 that we wanted to transmit. Consider that a single character is 1 byte of data. Thus, it's 8 electrical wires. This can become a mess of wires really fast. To make this more efficient, we need to use fewer wires and then have both hardware chips agree to a specific digital protocol and configuration that will be used to transmit data. Let's look at some of the most common protocols and how they work to send data still while reducing the number of wires needed. USART, Universal Synchronous Asynchronous Receiver Transmitter Communication. Ooh, big word. Okay, or as it is better known, serial communication. Well, that's a lot. Why didn't you just say that from the beginning? This is a protocol that uses 2 wires, 2 single wires. One wire is used to transmit data from the device A to device B. The other wire is used to receive data from device A from device B. In essence, we connect the transmit port to one of the devices and the receive port to the other device and vice versa. What is interesting about this protocol is that there is no clock. So no clock that synchronizes the communication of the devices. Without a clock, the devices have to agree to the configuration of the communication, such as the following: the communication speed, the bits per transmit, stop and start bits, and parity bits. So what are these things? Communication speed. This is also called the baud rate or the bit rate, and it dictates how fast bytes of data can be sent. Agreeing to a specific rate tells each device how fast it should sample the data to get accurate communication. While there are fixed standards for baud rates, devices can choose to use any other rate as long as both devices support it. All right. Bits per transmission. This is normally set to 8 bits, which make a byte, but it can be configured in something else, such as 16 bits. Stop and start bits. Since there is no clock, one device has to send a signal to the other device before it can send or end the transmission. The configuration of the start and stop bits dictate when and how this is done. Parity bits. Since there can be errors in the communication, parity bits can be used to detect and correct such errors in this transmission. That's all simple enough. Once the 2 devices agree on the configuration of the serial lines, they can now communicate with each other. A single transmission is shown in a diagram below on how an ASCII character of S would be transmitted. Let's scroll up. There are a couple of caveats, however. The devices don't really have a way of determining if the other device is ready for communication. To solve this, some USART connections will use 2 additional lines called clear to send or CTS and request to send or RTS to communicate to the other device whether it is ready to receive or ready to transmit. Furthermore, to agree upon what voltage level is binary 1 or 0, a third wire called a ground wire is required to allow the devices to have the same voltage reference. However, despite all of this, USART is an incredibly popular protocol in microprocessors due to its simplicity. Okay. Well, that's good. All right, now we got SPI. So what is SPI? SPI is the Serial Peripheral Interface Communication Protocol, is mainly used for communication between microprocessors and the small peripherals such as a sensor or an SD card. While USART communication has the clock built into the transmit and the receive lines, SPI uses a separate clock wire. Separating the clock wire from the data allows for synchronous communications, which is faster and more reliable. So the trade-off is adding an additional wire, but we gain a speed and reliability boost. An example of the S, or the same, being transmitted using SPI is shown below. All right, let's scroll up. The clock line tells the receiving device exactly what it needs to read the data line. Two-way communication is also possible, but quite a bit more complex than serial communication. Essentially, one of the devices is labeled the controller. This is the only device that is allowed to send clock signals. The other devices become secondary devices that must follow the controller's clock signal to transmit data back. If two-way communication is used, instead of having a single data line, two lines are used, namely peripheral in controller out, or PICO. This means communication is sent from the controller and the peripheral out controller in, or PoKey, which means communication is sent from the secondary device back to the controller. Using this, the controller sends a clock signal and a command out to the device using the PICO line, and then keeping the clock signal, the controller receives data back on the PICO line, as shown in the diagram below. Okay, there is one additional change that can be made. While there can only be one controller, there can be multiple secondary devices. To save wires and ports, all devices can use the same SCK, PICO, and PoKey lines. A fourth wire, called the chip select wire, is used to distinguish the device that the communication is meant for. The controller can use the line to indicate the specific device that it wants to communicate to it, as shown below. SPI communication is a fair bit more complex than USART, but having a dedicated clock line increases the speed at which we can communicate and improves reliability. Well, that's always good. So we can communicate faster and it's more reliable. I2C. The Integrated Integral Circuit Communication Protocol was created to deal with the drawbacks of both USART and SPI communication protocols. Because USART is asynchronous and has the clock built into the transmit and receives lines, devices have to agree ahead of time on the configuration of the communication. Furthermore, speeds are reduced to ensure communication remains reliable. On the other hand, while SPI is faster and more reliable, it requires many more wires for communication, and every single additional peripheral requires one or more chip select wires. Man, that's a lot. I didn't think about that. So, I2C attempts to solve these problems similar to USART. I2C only makes use of two lines for communication. I2C uses a serial data, or SDA, line and serial clock SCL line for communication. However, instead of using a chip select wire to determine which peripheral is being communicated to, I2C uses an address signal that is sent on the SDA wire. The address tells all controllers and peripherals which device is trying to communicate and which device it is trying to communicate to. Once the signal is sent, a data signal can be used to send the actual communication, to notify other controllers and peripherals that communication is taking place and prevent these devices from taking over from each other. A start and stop signal is used. Each device can monitor these start and stop signals to determine if the lines are busy with communication. An example of such data transmission is shown below. Since the external clock line is used, communication is still faster and more reliable than USART, and while it is slightly slower than SPI, the use of the address signal means that up to 1,008 devices can be connected to the same two lines and will be able to communicate. Now that we understand the basics of hardware communication protocols, we can look to analyze the logic of the rogue implant. I don't know if we understand the basics, but we definitely went over them, right? All right, probing the logic. After sending the rogue implant to the forensic lab for analysis, the following circuit diagram is uncovered. Based on the diagram, it seems like there is a microprocessor that is connected to the ESP32 or 32 chip. Doing some research, we can see that the ESP32 chips allow microprocessors to communicate over Wi-Fi and mobile networks. So whatever this implant was doing, it was definitely communicating with someone else. If we can intercept the communications between the microprocessor and the ESP32 chip, we would be able to see what commands and information are being sent. It seems like the perfect opportunity for our red and blue team to team up. Elf Forensic and Elf Recon are on the job. All right. The elves realize that these chips probably use digital signals that can be intercepted with a logical analyzer. Looking at the wires between the chips, we see a black wire connected to a pin called ground. We see a red wire connected to a pin called bin. Elf Forensic knows from experience that this would be the ground and the voltage in wires, respectively, meaning that these wires are used to provide power to the chip. Then that leaves green and purple wires that would be used for data transmission. Seeing that they are connected to the RXO and TXO pins, which would be what? Receiving, transmitting. Elf Recon can deduce that this refers to the transmit and receive lines of USART communication. Hence, we are pretty sure that the protocol used for communication is USART. Armed with this information, the elves connect the probes to the logic analyzer to the green and purple lines before powering on the implant. Immediately, super fast signals are seen on the analyzer. The elves create a logic data dump from the signals, and Elf McSkidy is asking you to investigate what actually was transmitted. All right, now we need to analyze the logic. In order to analyze the logic data dump, we need to use a logic analyzer tool called Analyse. Start the machine attached to this task, which we've already done, which will open an in-browser Windows machine where all the required tools have already been installed for you. Once the machine is loaded on the desktop, double-click the Logic 2 application. Once loaded, you should see this screen. All right, we've got our screen up. Scroll down. Let's import the logic dump to start our analyzer. Select and open the capture of Santa. So open capture. And let's grab, I think it was on the desktop. There it is, Santa. Go ahead and hit open. Decompressing the capture file. You can ignore the calibration error pop-up. Once loaded, you should be able to see the captures. If you hold the left control and use the mouse while to zoom out a bit, you can click the zoom X out. You should be able to see the digital signals. DO and D1 refer to the digital channel of the two lines that were probed. AO and A1 refer to the analog data from the probers. Hover your mouse over the thick line on D1, channel 1, and use the left control and the mouse wheel to zoom in again. You should be able to see the entire signal transfer. So we got D1, channel 1, left mouse, what is very interesting from the screen is that you can see how the analog voltage data corresponds with the digital signal that is seen. Look at A1 channel 1 versus D1 channel 1. You can see that there are slight breaks in the analog data that have been corrected in the digital data in the digital channel. Now we can see the digital signal data. We can look at the logic analyzer to read contents of the data. Click on the analyzers tab to the right. Okay. Since we know the protocol is USART, let's look at to configure the async serial analyzer for both channel 1 and 0. Let's configure channel 1's analyzer first. If we were true hardware reverse engineers, we would first have to figure out the rate in which the data is being transmitted, as well as the specific configuration such as the parity bits and frames. However, to keep this simple, Forensic Elf has already discovered this for you. Alter your configuration to match the following and click Save. All right, so let's click Async Serial. And we're going to do channel 1 at 4800. I think we've got 8 bits, none, 1 stop, no parity, least, none. That should be good, and let's hit Save. Ooh, look at this. Now we've got data in this bad boy. All right. Once saved, we can see that there's data being analyzed. Click the little terminal icon, and we can actually read the data being transmitted. No way. Ah, there we go. So we see our data being transmitted over here. Okay, we see the initialization sequence of the serial line and then 3 lines of data being sent. ACK reboot. We see CMD X195837. Okay, and then we see 9600, which looks like 9600 is the baud rate, if I was going to guess. This doesn't yet mean anything since we are only seeing one side of the data. In order to see the other messages, we need to add another analyzer to channel 0. Click the plus icon next to the analyzer and add another asynchronous analyzer with the same configuration except for channel 0. And everything's the same, so we'll go ahead and hit save. Now we're starting to piece together the information. It seems like the microprocessor is establishing a session with the ESP32 device to allow communications to the control server. Now we can see the full discussion between the two devices. The processor asks the ESP32 to reboot its connection to the control server. The ESP32 is happy to oblige, but requests a security code to be sent to allow connection over to the control server. Once the security code has been retransmitted, the ESP32 allows the microprocessor to negotiate a new baud rate to be used for communication. Interestingly, once the new baud rate is accepted, we cannot read the rest of the output.
Emotional damage.
However, since we intercepted the baud rate, we can simply edit channel 0 analyzer to a new baud rate and read the rest of the communication that was sent. And if we make that change, we'll get to see our flag.
And there it is. Who's the best hacker in the world, people?
All right, let's go over here and edit. And if we change our baud rate to 9600, and save it. And there we go. Down here at the bottom, we now see our new flag. So we got them. Okay. So there's our flag. This is excellent progress. We were able to read the initial communication between these two devices that were used to establish a connection to the control server. Now we have this information. We can keep monitoring the lines and analyzing the logic to see any messages that are sent. We are now one step closer to knowing who is responsible for this rogue implant. All right, let's see if we can answer these questions. What device can be used to probe the signals being sent on the electrical wires between the two devices? Well, that was a logic analyzer. All right. USART is faster than SPI for communication. Let's see. I don't remember. I don't think so. So if we remember back, USART, SPI says it's faster and it's more reliable. So I'll say nay on that one. Make sure we have the right. All right, perfect. USART communication uses fewer wires than SPI. That is yay. USART is only using 3 lines, an in, an out, and a ground, I believe. Yeah, so we had the transmit and the receive. So transmit and receive, and then we have a third wire called the ground. So there it is. All right, USART is faster than I2C for communication. I'm going to go with nay on that one. I2C uses more wires than SPI for communication. That again is nay. SPI is faster than I2C for communication. That is going to be yay. SPI is faster and more reliable. What is the maximum number of devices that can be connected on a single pair of I2C lines? I think we remember that one. That was 1008. What is the new baud rate that is negotiated between the microprocessor and the ESP32 chip? If we remember correctly, we started off with 4800 and then they doubled that, so it's going to be 9600. And what is our flag? So our flag, there's our flag. Hacking hardware is fun. So if we're looking for a challenge, try our recent threats module. We'll go ahead and hit complete on that one. So that completes day 19 of the advent of cyber. Tomorrow we'll come right back and do it all over. Until then, I will see you guys.